everyone. So today's lesson kind of digs into a few other types of integration topics, and honestly, this video is just going to focus on the first of those, which is this first page. And this is adding just one extra step to the U-substitution process that we've been talking about. So if you remember, what we've been doing so far with U-substitution is just finding antiderivatives, right? We've been stopping at a place where it's like an equation with a plus c in it, and that's a generic antiderivative. We've been doing integrals that don't have endpoints on them. We've been doing indefinite integrals. Now we're going to talk about doing definite integrals where we have actual numbers to plug in. We technically could get away with doing the process exactly like we just did, like we've been doing for the last couple of days, and then plug in our endpoints of 1 and 2. But there's actually a way to shorten up the process, and it makes a little more sense notation wise to write it this way. So I'm going to encourage you to do it this way because otherwise you could potentially lose points in your notation if you were trying to write this process out. But let's just start with what we've done so far. And if you would like to, you could pause the video now and try the U-substitution process on this first problem. Just pretend it was, ignore that 1 and the 2 for right now. Pretend it was just another integral where you're trying to find an antiderivative. Let's see how far we can go. So I'm going to start with the 4x minus 1 as being my u. And then I'm going to take a derivative, which would be 4, and that gets a dx on it. And then I'm solving for dx. So I would move the 4 to the other side, and I would say this is 1/4 du, and that equals dx. And now I'm going to come back up here, and I'm going to rewrite my integral. Now I want you to notice that I'm not putting my endpoints in right now, and there's a reason for that. We'll talk about that in a minute. But I'm going to now call this a square root of u. Okay, I'm replacing this with u. And I'm replacing my dx with this thing down here. So this is 1/4 du. And my next step, now my notation is still a little faulty here, but we'll come back and fix it in just a minute. But my next step, and this is the step that a lot of people forget, is to actually take an antiderivative. That's what this thing is telling me to do, right? Well, I know that this 1/4, I mean, I could technically pull it and put it out front here, but that's going to just be part of my antiderivative, right? So I'm going to have 1/4 times. Now let's do antiderivative of the square root of u. Well, that's u to the 1/2. I'm going to add 1 to the exponent, so that gives me u to the 3/2. And then I'm going to do the reciprocal down in front, so this is going to be a 2/3 u to the 3/2. Then I could maybe clean that up a little bit. Let's see. 1 times 2 is 2, and 4 times 3 is 12, so that would give me 2/12, otherwise known as 1/6 u to the 3/2 power. Now, I want you to pause right here, okay? Because as far as what we've been doing for the last couple of days, our next step would then be to take this 4x minus 1 and put it back in here for u. And we could do that. We could put the 4x minus 1 here and then evaluate that from 1 to 2. But there's actually sort of a shortcut I can take. I can stop right here. I can use this as my antiderivative, and I can say this is what I'm going to use to evaluate my endpoints. But the trick to this is I have to adjust my endpoints, okay? And I'm going to adjust my endpoints using this relationship with u, because this is an integral in terms of x, and this is an antiderivative in terms of u. So I need to take these endpoints that used to be x's and turn them into u's, okay? Now, honestly, I probably wouldn't take the time to write this next step out. I'm doing it just for your benefit for this video so you can see what I'm doing. But my first endpoint is going to be 4 times 1 minus 1. I'm just putting the 1 in for x here. So let's see, that's 4 minus 1 is 3. And then I'm going to go 4 times 2 minus 1. Well, let's see, that's 8 minus 1, which is 7. And so that means my endpoints over here for my antiderivative are from 3 to 7. Okay, I should have done the 1 on the bottom just because it was on the bottom here. But this is the idea, is that I'm taking my endpoints and I'm plugging them into this function for u. Okay, and so over here, when I go to evaluate this thing, gosh, do I need another color? I think I do. I'm going to get something that just looks like this. 1/6. I'm going to put the 1/6 in front of everything. And then I'm going to put the 7 in place of u, and I'm going to put the 3 in place of u. So I would get 7 to the 3/2 power minus 3 to the 3/2 power. Now, I have no idea what either of those is. I'm doing this without a calculator, and those don't, go to the 3/2 power very well because they're not perfect squares. So realistically, I'm just going to leave my answer right here. But I want you to understand that this is the same thing we would get if we had plugged this u value in here and then plugged in just the 1 and the 2. It's really just a difference of when are you putting the 1 and the 2 into this 4x minus 1. Okay? The reason this method is preferable is that right here, when I wrote this equivalency statement, when I said this is equal to this, I technically can't say this thing here in blue with a 1 and a 2 because those are not the same thing. Once I convert this to u's, my endpoints have to convert as well. Okay, and so really I wanted to kind of walk through this process because you already knew how to do all of this. So I didn't stop to do this back here. But in this process, what I should have done is converted these right away. I should have said, okay, 4x minus 1, so 4 times 2 minus 1, that's 7. And then 4 times 1 minus 1, that's going to be 3. And then those would have been my endpoints all the way through the rest of my problem. Okay, so let's try that on this next one. Okay, I'm seeing a definite integral from 0 to 2. I'm going to start the same way I always do. I'm going to start by finding my u. My u is 7x plus 5. This next part's pretty predictable because this is a pretty basic one. My derivative is just 7, which means my, whoops, I'm getting ahead of myself here. This is going to come over as a 1/7 du equals dx. And then I'm going to go up here and rewrite my integral. So I'm going to say this is an integral, and now it's going to be cosine of u times 1/7 du, because that's going in for my dx. And now I have this in terms of u and this in terms of u, and that's great. Now I need my endpoints in terms of u as well. Okay, so I'm going 7 times 0 plus 5. Well, that's just 0 plus 5. And that's what's going here. And then I'm going 7 times 2 plus 5. That's 14 plus 5 is 19. 19 goes here. And again, realistically, you probably wouldn't actually have to write that out. I'm doing that just so you can see what I'm doing. Okay, so my new endpoints are 5 and 19. And now this statement is a true statement that this integral is equal to this integral. If I had kept those endpoints the same but left this in terms of u, I'm technically making a false equivalence, and we would get in trouble notation-wise on the AP test for that. So just be careful there. Okay, so now let's do the antiderivative step, right? Don't forget the antiderivative step because that was the whole point. The whole reason we did this was to get something that we could take an antiderivative of. I can take an antiderivative of cosine, it's sine, and then this is going to be a 1/7 in front, so I'm going to have 1/7 sine of u. And we could go through and put our u value back in here of 7x plus 5, but then we have to convert our endpoints back. It's way easier just to say this is going to go from 5 to 19. Okay. And then as far as my answer goes, and again, I would probably just put this on the end here. Actually, maybe I can fit it in for this one. I would leave the 1/7 in front of everything. And then I would just say sine of 19 minus sine 5. And again, those are not perfect values. Those are going to be some crazy ugly decimal. I would leave my answer just like that. Okay. Okay, so let's take a look at this next one. This next one, I think we actually can do something with the endpoints here. Okay, here's a little trick to this one. And I don't know if we've seen one of these yet. Can't remember. Let's think about our u. Our u is going to be this 2x that's kind of buried. So u is 2x, which means du is 2 dx, which means 1/2 du is equal to dx. Okay. What's going to be really important in this next step, because some of you might already be looking at this and going, well, wait a second, this looks like cosine squared is the inside function, inside a 1 over whatever. 1 over cosine squared is really just secant squared. Okay, that is a big deal, is understanding that this thing here is really just secant squared in disguise. So when I write this integral, I'm not going to write it as 1 over cosine squared because that's not something I recognize, but I do recognize secant squared of u, right? And then my dx is 1/2 du. And let's adjust our endpoints, okay? So our u is just 2x. So my 0, if I put 0 in here, is just going to stay 0, right? That 0 is not moving anywhere. But if I put pi over 8 in here for u, 2 times pi over 8 is really going to be pi over 4. Okay, if you don't believe me, 2 times 1/4, I'm sorry, 2 times 1/8 is equal to 1/4. Okay, so now let's do our antiderivative. And this one we can get down a little further. Don't forget the antiderivative step. I'm going to have my 1/2, right? This is going to go in my answer. Antiderivative of secant squared would be tangent. And again, instead of subbing that u back in, I'm just going to keep it as a u and use my new endpoint. So I'm going to say it's 1/2 times tangent of u taken from 0 to pi over 4. Okay, so I promised you this one we could go a little further. I am going to go down to the next line here, but I'm going to say it's 1/2 and then it's tangent of pi over 4 minus tangent of 0. Well, let's test our trigonometry knowledge, shall we? Tangent of pi over 4, that's going to be your middle dot in the first quadrant on the unit circle. And your tangent there is equal to 1 because the x's and y's, the sines and cosines, are exactly the same. And tangent of 0 is just 0. So this is really 1/2 times 1 minus 0, which ultimately is just equal to 1/2. Okay, so that's how these are going to work, is instead of plugging the u back in, you're just going to adjust your endpoints earlier in the problem. And then when you do that antiderivative step, you can just evaluate that antiderivative from top to bottom and subtract like you were before. Okay, one more to get through. And this might be another good one for you to pause and try on your own before you continue watching the video. I'm going to take this thing on the inside and call this my u. So u is x squared plus 2x minus 3. This one's going to be a fun one to adjust my endpoints with. Du then is 2x plus 2 dx. And so then for my dx, it's going to be 1 over that 2x plus 2. Squeezing it in down there. Du equals dx. Okay. So rewrite my integral. And my endpoints for my integral, I'm putting the 1 down in here for x, and it's going to go in 2 places, right? So I'm going to do 1 squared, which is 1 plus 2 times 1, so that's 3, and 3 minus 3 is 0. Let's do the same thing with the 2. So 2 squared is 4, plus 2 times 2, that's another 4, so that's 8, and 8 minus 3 is 5. So my new integral, when I'm working in terms of u, will go from 0 to 5. Okay, and now I have u squared times this x plus 1 times this 1 over 2x plus 2 du. Okay, well, the whole point of doing this was to get rid of my x's. So I need to think about how I can get this x plus 1 to cancel. And I hope that you're screaming at me behind the screen here that this 2x plus 2, if I factored it, I could make an x plus 1, right? I could take this 2x plus 2 and say, well, this is really 2 times the quantity x plus 1, like if I factored out a 2. And then I've got an x plus 1 that cancels with an x plus 1, and I have a 1/2 kind of lingering here in my answer. And now I'm doing an antiderivative, okay? And sometimes when there's these intermediate steps where you have some other stuff going on, I think we tend to forget the antiderivative step. I see a lot of people who just want to throw u back in right now, but we haven't done this part, right? This was the whole point of what we're doing, is to take this antiderivative, okay? So let's take an antiderivative. First of all, I'm going to have the 1/2 that I circled here in my answer. So 1/2 is here. Okay, that's from here. My x's are gone. My x plus 1s are gone. My antiderivative of u squared is going to be a u cubed with a 1/3 in front of it, right? Add 1 to the exponent and then divide by that new exponent. And that, well, that's really 1/6 u cubed taken from 0 to 5. And now those are my endpoints that are going in place of u. And really what I want to remind you is that u is this thing. So whether we did it here when we switched it from 0 to 5, or whether we had put this u thing back in and kept it from 1 to 2, at some point we're going to be doing what we did right here, where we put the 1 in here and we put the 2 in here. Okay? And so that's why it doesn't really matter, but your notation gets kind of choppy here if you don't convert those endpoints, because you can't talk about this integral in terms of u without switching the endpoints. Okay, let me finish this one off. I'm going to leave the 1/6 in front, and now I'm putting in the 5 and putting in the 0, so I'm going to have like 5 cubed minus 0 cubed. Well, 0 cubed is really just nothing. And so this 5 cubed is 125. So this would all simplify down to 125 over 6. Okay. So that was really the point of today. It's still just U-substitution. But the big new thing is understanding how your endpoints switch when you're working with a definite integral. How do I get these new endpoints? And the short answer is your original endpoints were in terms of x. So you just use this u statement to convert your endpoints to something in terms of u. Okay. So we're going to give some of those a try tonight, and then we will have more integration fun coming up for us later this week.